Okay, this is a video about an extremely rare occurrence that will happen in statistics, and it is dealing with the situation where you know the sigma or standard deviation for a measure of the population, but you don't know the mean. So we do know the standard deviation, but we don't know the mean. And we're trying to estimate that mean. Okay? Here, you follow exactly the same procedures that you would normally follow for a t-test, but you're going to use a z-test on the calculator. Okay, so what we're going to do is we're going to test a claim that the height of supermodels is greater than 63.8 inches. So my H null here is going to be that the mean is 63.8 inches because that has to be an equivalent statement. The alternate hypothesis is that the mean is going to be greater than 63.8 inches because that's my claim, that they're taller than 63.8 inches on average. Okay, but we're going to suggest that I happen to know that the standard deviation for heights for this population is 9/10 of an inch. That they're fairly all bunched up around the same height. Now, we take a sample of, let's say, 10 supermodels. And the reason why I can take such a small sample is that we can assume that height is normally distributed because height is normally has a central tendency around some mean in a bell-shaped kind of way. So my sample size is 10, and we're going to say that the mean of the sample was actually 70.035 inches. Okay, and this is sufficient enough to run a z-test on the calculator, knowing the size of the sample, the mean of the sample, and the standard deviation of the population. So let's actually get that in the calculator. Okay, because I know the population standard deviation, I'm going to go to stat tests. Instead of picking t-test, I'm going to pick number 1, the z-test. And I'm working from statistics. So I'm testing against a claim of a height of 63.8 inches. The standard deviation for the population is 0.9. I took a sample and got 70.035 inches, right? So I had a sample size of 10, and this is a right-tailed test because I'm testing greater. Okay, so just so you know where these numbers are coming from, that 63.8 is like average female, all right? And this is like supermodel sample. So we're saying that the supermodels are in general taller than the average female. We calculate, and like the p-value there actually sinks to 0, which means yes, that p-value is positive, but the calculator has it so close to 0 that it said, oh, that's 0. It rounded it to 0. So p is definitely less than 0.5. It's very, very tiny. When p is very, very tiny, we reject the null hypothesis. So let's look back at our original idea here. The null hypothesis was the equivalence, right? So the claim is the alternate hypothesis that the height is larger than 63.8. So this result would support the claim that the supermodels are taller on average than 63.8 inches, which means that they are taller than the average woman. All right, so there you go.